Welcome to our YouTube channel. In this video we are going to look substation gantry structures design philosophy. In every substation project, the tallest structure is the gantry structure. So in order to design the gantry structure, we need this preliminary input. First one is electromechanical principle drawings. This will define what kind of structure we are going to do design. It will give the span of the girder, face to face distance of the conductors, and conductor fixing height from the base, earth wire fixing height above the conductor fixing level. It will provide you plan, layout, section drawings. So in that section drawings we can able to find out the total height of the structure, gantry structure, that including body plus peak. Here in the right hand side picture you can see body is nothing but from the base to the conductor fixing height is called body of the gantry structure, and from conductor fixing height to the earth wire fixing height we can call it as peak. Sometimes this peak won't be there in the gantry structure because of the absence of earth wire which is to be run in the top of the tower. In some cases, instead of earth wire, there may be also possible to keep a spike rod above the tower. So in the plan view you can see here next picture in the right hand side. So this is a tower view in the plan. This is a girder which is connecting the two tower. So this information we can able to get from the electromechanical principle drawings. So total height, body and peak, and the number and the span of base. So in the electromechanical principle drawings we can able to identify whether this is limited to only two towers and one girders, or it is going to extended to another bay. So this will provide you the number of bays and span of the base. Span is nothing but distance between the center to center distance of towers. Then the next one is conductor details is another input we required. So there are four types of conductor in the market: AAC, triple AC, ACSR, ACAR. AAC is called as all aluminum conductors. Triple AC is all aluminum alloy conductors. ACSR is aluminum conductors with steel reinforced. ACAR is aluminum conductor with alloy reinforced. So there are four type of conductors in general. In most of the substation projects we used to have ACSR type. Even in the transmission line also this ACSR is the predominant conductor. Size and span and weight of the conductor is required. So this we can able to get from the conductor catalog. Tension and short circuit forces, we need to arrive this by generally this tension is mainly applicable for the conductor and earth wire because of their long run span. Because of their flexible nature, the conductor tends to sway due to the self weight, wind, snow or ice, or even in the temperature. So these are the four main parameters like temperature, wind, snow and dead weight and self weight. Due to that the conductor will tends to have some sag. In order to arrest the sag, there will be a tension to be applied in the both the end of the conductor. So this will impact on structure girder. So that the tension value also we need to calculate. Generally the tension value in the country where there is no snow and temperature, minimum temperature is not envisaged. For that condition we can consider only the dead weight of the conductor and applying the formula WL square by 8, where W is the unit weight of a conductor in kg per meter and L is the span, total span of the conductor. So this WL square by 8 formula we need to apply to calculate the bending moment of the conductor. As the conductor, I said earlier, it is a flexible, we need to apply a sag percentage also. So by dividing this bending moment by a sag value, that is generally in long run conductor we need to consider 5% of sag. So 5% of total span to be divided to the bending moment, so that we will able to get the sag tension values. So WL square by 8 is a bending moment. In that we need to apply the sag value of 5% of total span. Generally the bending moment is in kilonewton per kilonewton meter, sag span in meter. So kilonewton meter divided by meter will cancel the meter and we will get the value in kilonewton. So that is sag tension. So likewise we can calculate the tension values initially. R depends upon the area and the stress value which is provided by the conductor manufacturer. We can also find the tension value. It's nothing but applying the stress value multiplied with the net cross-sectional area of the conductor, we will get the tension value. Another one is a short circuit force, is a electromechanical force that should be calculated by an electrical or mechanical engineer by applying the fault current and face-to-face distance and ground clearance. So there are various parameters. Being a structural engineer, we no need to concentrate on these short circuit force calculations. Next one is deviation or tilt of conductor. So in the plan you can see there is a tilt of conductor in various phases. So you can see here in plan the conductor are tilted from the normal conductor span. So it is said that it is a 30 degree. So this is a general way of conductor span, vertical direction in the plan, but this conductor is deviated. So this deviation is called horizontal deviation, and you can see in the right hand side picture the elevation. So here you can see the conductor is sloping downward from the normal vertical arrangement of the tower. So this is called vertical deviation. So in most of the substations, this vertical and horizontal tilt should not be greater than 30 degree. So this is earth wire. So this kind of vertical deviation is applicable where the substation is at higher level and the transmission line is at a lower level. Then this kind of downward vertical deviation or tilt is possible. But in generally in most of the cases, when the terrain is plain for both the transmission line and substation line, then there will be only the vertical upward tilt, because the transmission line generally used to have taller than the substation tower. So the vertical tilt is in upward direction only. Next input we required is hardware details, that is suspension and tension insulators. In that we need the length, size and weight. Environmental design loads such as wind, seismic, snow, temperature. Generally that seismic we can ignore by just comparing with the wind in most of the projects, but some customer used to ask us to calculate both the seismic and wind load calculation in separate load combinations. So if it is requested from the owner of the project, we need to do obviously, or else we just compare this wind and seismic impact. Generally that wind impact is more in gantry structures because of their exposure categories to wind is more when compared to seismic. So it is better to just compare the forces of wind and seismic, and if we find that wind is more as a predominant, then we can ignore the seismic calculation furthermore to doing with the load combinations and other parameters. Next one is standards to be followed. This is another preliminary input. So here the standard means that loadings, what kind of which standards to be referred for loadings, design and material standard, like ANSI, which is an American standard, Eurocode, SNP is for Russian standard, BI is British standard, BI is Indian standard, likewise Philippines, Indonesian, Argentina, Algeria. Whenever the seismic prone area or heavy wind area like Indonesian, Philippines and some peninsula project, we need to go with the loadings calculation based upon their domestic standards. Say for example, Indonesia used to have heavy wind loads, and Philippines also used to have more wind and cyclonic load or a seismic load. So in that criteria we need to consider the standards of domestic, and the design material we can also follow the global standards like ANSI, Eurocode or Russian standards. Next input is supplier catalog for available profile or sections. So this is very important when we are doing project for overseas or doing the project with various supplier. If the supplier is going to change, we need to check with them whether this materials which we are going to do the design freezing. So before design freezing, we need to check with them whether they are having this the profile available, because some supplier used to have 6 meter of certain sections which is not available in 3 meter or more than 6 meter. So we need to provide splicing in this kind of criteria. If it is that exact the required span is not available with the supplier, we need to provide splice in our design consideration. So next philosophy we need to find out is mechanical components of structures. So for gantry structures, these are the mechanical components. Start with the string or tension insulators, conductors and its spacers. Generally spacer is not required if the conductor is having only one number of conductors. That is, for single conductors the spacer is not required. Dropper or jumper, suspension insulators, earth wire or ground wire or spike rod, lighting and lighting fixtures. So in the right hand side picture you can see a red circle. So this is the dropper. Dropper is nothing but it is a connection between the running line which is connected to the gantry and to the equipment which is just below the gantry. So here you can see there are 3 phases of dropper which is connecting from the line conductor to the equipment just below. This equipment is a current transformer. So this main purpose is to measure the current flow of this line. And in the other side, that is in substation side, actually this CT is placed in the transmission line side. Other side you can see this dropper is connected to disconnector. So you can see here 2 pole of insulators. So this is a dropper in the substation side, so it is connected to a disconnector. And the blue color circled components are a tension or string insulator. So in this type of connections there is no jumper or suspension insulator. So this left hand side downside. So this cross section is a sample conductor cross sections, and this is a earth wire. So lighting and lighting fixtures generally, in order to some of the project, in order to avoid the light mast structure, some customer specifies to fix the light on the gantry structures, that is line or substation gantry structures itself. So for that we need to consider the dead weight and wind acting on the lighting fixtures and the lights. So earth wire or ground wire, generally it should be fixed on the top of the tower, but in this case spike rod is provided. So we can see another picture illustrating these mechanical components. So here from the top in this picture, this is earth or ground wire or shield wire. This part is a tension or string insulator. This component is jumper, which is connecting the in and out conductor using a suspension insulator. So these are the conductors. So this is a line in conductor. So this is line out conductor. You can tell it as this is input from the transmission line, and this is substation side. So this is a dropper which is connecting to nearest equipment, and this is a girder which is holding the three-phase conductor and its hardware. This is a 765 kV tower which is connected with the quad, that is 4 number of conductors and twin insulators, string insulators, and 1 set of suspension insulators. So this number of insulators required is depends upon the conductor type and its connector. So sometimes even we can also connect with the single insulator with the twin conductor, that is double conductors. In some case 2 tension conductor is required to connect the cord, that is 4 number of connector. So it's depend upon the insulator capacity to hold the tension to be applied in the conductor. Similar like the suspension insulator, generally don't have any high tension requirement, so that it can be a single insulator. So similar like this, one set should be have in all the 3 phases. So this is another view of mechanical components of gantry structures, so which is taken before the installation or charging. So here the dropper is just fixed, and suspension insulator also just fixed without connecting with the jumper. So this is a view of a dropper connecting to surge arrestor. Surge arrestor generally used to keep to measure the surge count. It usually used to have some limitations like 50,000 count or likewise. So after that it will get the problem are ready to replace. So the replacement to be done. So this is another dropper which is connecting a disconnector. So this is a close view of tension insulators. Next one is a structure configuration. So these are the basic structural configuration for any of the substation projects. Bolded, you can see in the left hand side picture or center picture. So this blue color structure is a illustration of bolded structure configuration, whereas all the bracings, diagonal bracings and the horizontal bracings to be connected using bolts. Even the splice of leg members to be connected by bolt. The girders connections are also to be done in bolt. So this is a picture for welded connection, whereas you can see all the 4 legs are connected by plates with welding connection. So here the girder also connected to the tower with the weld. Generally this girder used to connect with the cross arm also. Semi welded is nothing but one side it could be a weld and another side of the bracing it may be done with angle section, inclined angle section with bolt connections. So this kind of semi welded is applicable where there is a high conductor deviation in horizontal plane. This photo of a substation tower is for guide wire type. You can see a guide string wire is tied to the ground from the girder fixing of the tower. So in the left hand side you can see the anchoring of the tower guide wire on the ground, and backstay is in the right hand side you can see a frame tower which is holding the girder having a tripod connection. So this support is used to call as backstay. So this kind of arrangement, this backstay is required where the conductor is deviated in horizontal plane direction. So these are the main structure configuration in any of the substation projects. Depend upon the requirement or the working principle of the construction management, we have to decide which kind of structure configuration is better, because in bolted connection is better for in case of replacement of any parts, it is possible with the bolted connection. But in welded connection there are some challenges. We cannot able to replace the project instantly. We have to break the entire weld, and modification is not possible once after erecting. So likewise guide wire, even the this advantage of welded connection is we can able to done at factory itself, and simply the installation at site is very easy. So guide wire will give you the reduction of steel weight, because all the main structures, that main leg to be connected using a guide wire, which is cheaper when compared to the steel structures. Backed stay also reduce some steel weight, but steel instead of weight it will give you less labor work during installations. So next one is design procedure. So for the design procedure, these are the steps. There are 12 major steps involved. One is primary loads. Primary load is nothing but it is a dead load, calculation of dead load, conductor tension, wind loads on XY direction or the diagonal wind, seismic if it is applicable or required for the project as per technical specification, snow, temperature loads, ice loads, and if any other loads. So these are the primary loads we need to calculate. Next one is load combinations. Generally this to be followed as per technical specification or any consultant provided input or standard codes to be followed. And after calculating these two, we need to model it in 3D analysis software, applying loads, the calculated preliminary and the primary loads in the 3D model which we had prepared, and apply the load combinations in 3D model, run the analysis. And before going to assign the member size, we need to check slenderness. Generally the slenderness formula is 1.2 into height of individual member, that is connecting member, where this member is going to connect, that height we need to consider, divided by radius of gyration I. Generally in most of the standards, or either it is a European or American or Indian standard or Indonesian standard or whatever the standard, even in the Russian, they used to provide the slenderness limits. 120 is a slenderness limits for main leg, 200 is for primary bracings, secondary bracings it is 240, and horizontal members which are connected between the legs is 250. So what is primary bracing and secondary bracing means? Primary bracing will take the both the tension and compression loads. It will transfer to the main leg. But primary bracing, in order to, if you check with the secondary bracing will not take most of the load from the structure distribution module. It will act like a redundant member. So redundant member is nothing but if suppose the main leg height is going more than the expected, if it is going to fail in slenderness, say for 120, then we have to provide an intermediate bracing. So that is called secondary bracing. It won't take any load. It will just break the main leg span into 2 or 3. So that is called secondary bracing. And another one is horizontal beam. So generally this will have some tie between the main leg in horizontal direction. So it is not in the inclined form. So this will have 250 as a slenderness. So likewise we need to check it. After that only we can able to get which the profile is suitable for main leg or primary bracing or secondary bracing or horizontal beams. So if you choose from this method, means it is very easy for you to finalize the section or member properties. So after that you can feed this member properties into the 3D software, or if you want to do the manual calculation also, you can do it for design of structural members. That is a 8th step. After doing all the calculation, you need to check for deflection. So the deflection limits is height divided by 100. It means the total height of the structure, that is a tower, to be considered for H, and the same to be divided by 100. Suppose I am having a height of 10 meter tower, so then I have to divide it by 10,000 divided by 100. So I should have the value of 100 mm as a deflection limits. It means after all calculating this value, my actual deflection should not go beyond 100 mm. If it is go beyond 100 mm means the structure will visibilized as unstable. Then we have to do redesign by increasing the structural member profiles. Like suppose if I am having a main leg as 150 by 15 or 150 by 10, if my actual deflection is beyond the limited deflection, then I have to change this 150 into 160 by 16 or 180 by 15. Likewise, I have to do iteration process to be done until the deflection is passed. Next step is design of connection. So this connection design means splice connection for main legs. As I said that some supplier won't have maximum span of greater than 6 meter. So if your structure member is going to higher than the 6 meter, also we need to consider the transportation of maximum span, because if the project is going to constructed in hilly area, so the transportation is logistic is very difficult. Whereas if the narrow way is there means we need to check that also. So accordingly the splice connection to be provided for the main legs. And the next one is bracing member connections. So in this we need to check bearing, tension and shear. Base plate connections, we need to check tension and compression. Next step is extract support reactions for foundation design. So this is the input we need to provide for foundation design. Next final step is we need to design the foundation bolts or stub connection. In some of the project, instead of foundation bolts, we have to design stub connection. Stub connection is nothing but the entire main leg to be inserted in the foundation at the pedestal. So in some projects they used to go with the base plate which is to be anchored in the foundation pedestal. So for that we need to calculate design of foundation bolts. On the other hand, we need to calculate the stub connections. So these are the preliminary steps to be followed for design of substation gantry structures. So calculation of primary loads. As I said earlier, these are the various primary loads to be considered. So dead load means it will happen due to the conductor own weight, due to hardware weight, that is tension and suspension insulators, as we see earlier the picture about that, due to earth wire at the top of the tower, due to structure's own weight. Generally, if you are doing this analysis, the load applications in any 3D software means the structure's own weight can be considered by the software itself. We no need to calculate manually. Weight of man with kit, generally for maintenance purpose, one man with his kit used to climb on the structure to do maintain or do any check, frequency check on the insulators or any conductors or any equipment fit on the structure to be checked, or for the lighting fixtures. So we have to consider the dead load of a man with kit. Generally this will have some 100 kg or 1 kilonewton to be considered as per the customer requirement, or even for the standard codes used to specify these loads. So it is the point load to be applied on the critical locations. Suppose on the midspan we can consider this weight of man with the kit. Next one is string loads. So this is a conductor tension loads or pull loads to resist it, to arrest or minimize its sag due to self-weight or any other environmental loads such as wind, ice or snow, or temperature loads. So based upon these external loads, the conductor used to tense or create some sag. Sag is nothing but it is a sway or a deflection of any conductor. In order to resist or in order to minimize this sag, we need to apply the conductor tension on both the edges, because the too much of sag will leads to ground issues of ground clearance issue of any conductors. So for that a tension to be applied on both the side, so that the tension load also we need to consider. Next one is wind loads in a planar view, that is x and y directions. So in a plan view we need to apply like x and y plan view. And also some standards ask us to go for a diagonal wind also, either it may be 20 degree or 45 degree or 60 degree, because wind we cannot able to predict that whether the wind is going to act only in the perpendicular direction of the structure or parallel direction of the structure, that is x and y. It may also act in diagonal, so we have to calculate accordingly. For that we need to apply the cos or sin theta formula to be applied on the planar wind in x and y. So by that way also we can calculate the diagonal wind force or the pressure. And even in the wind load also, based upon the combination of ice or snow, it is categorized as extreme wind, high wind and moderate wind. So these three wind categories mainly applicable where the project or the structure is subject to ice or snow loads. Because when there is a ice or snow, we cannot able to consider the extreme wind, because that wind forces is going to reduce when there is a heavy or extreme snow is there. So in that case the load combination to be done based upon the extreme wind with no ice case, high wind with moderate ice or snow case, moderate wind with extreme ice case. So that load combination, based upon the load combination, that wind loads to be categorized as extreme wind, high wind and moderate wind. Then the next one is snow or ice loads. So this is mainly applicable for countries like European and American locations, and even in some of the countries we used to envisage this snow and ice loads. And the temperature loads, wherever the temperature is going to reduce, say for it is going for minimum temperature like below minus 20 or minus 40, especially in countries like Russia, European countries and America, the temperature will go beyond minus 40 degree. So if it is minus 40 degree, as the conductor connected is a longer span, say for example 50 to 100 meter from the transmission line to substation tower, this temperature, due to these temperature variations, it will tends to create more the pull or sag. So that temperature loads also to be considered while calculating the substation gantry structures, in where the temperature is going more lesser than the minus 20 degree or 40 degree. Next one is accidental load. This is a short circuit force which is to be calculated by a electromechanical engineer or electrical engineer or mechanical engineer. So this is based upon the fault current and the face to face distance of any conductor while it is swinging together. So at that time there may be a possible of touching of two conductors. So during that case, accidentally the conductor will produce a short circuit forces. That forces also we need to consider while doing the design of gantry structures. Generally, if the Substation tower, if it is going to connect to the transmission line tower, this short circuit forces can be ignored because of their conductor spacing or face to face distance is higher than the substation towers. So we can avoid this accidental load if the substation tower is connecting to the transmission line tower, or even in the transmission line tower design we can ignore this short circuit force, which may not happen in that. And finally, the seismic loads, if it is required by the technical specification or customer, or else we can ignore this also, because seismic load is very less impact when compared to the wind loads. Again, this can be applied in either X, Y horizontal direction or Z vertical direction, depend upon the requirement or the standards. Next one is design optimization. For design optimization, these are the parameters we need to consider while going for design of members. First one is dimensioning. Generally, the tower base to be dimensioned in such a way that the total height divided by 8. Suppose I am having a 16 meter of height of the tower, I have to divide that total height. That means body plus peak is to be considered as h. That is 16 meter divided by 8. I will be getting 2 meter. Then I have to have the maximum base width of 2 meter. If conductor deviation, so this base width. So if my tower is having so I have to, so this is my base width of the tower. So that maximum, so this is a minimum dimension and this is a maximum dimension. So this maximum dimension should be h divided by 8, and the minimum dimension depends upon the deviation of the conductor. If I'm having horizontal deviation up to 30 degree, means we need to increase this width, or else we can have the uniform width from bottom to top up to the connection of girders, or else we need to increase this. Similar like girder cross section also we need to define. So if the girder span is more than, if girder span, suppose I am assuming is at a 12 meter, then the span is L, 12 meter should be divided by the value 12, so that I can able to get the cross section width of the girder. So that 12 divided by 12 means I am getting 1 meter. So 1 meter is a cross section of the girder to be considered for economical design. In such a way, if the tower base is designed h divided by 8 and the girder cross section to be designed as L by 12, means it is a optimized design, whereas I can able to complete this design calculation with the optimized solution called the, whether the as the profile, the member can be optimized, that section can be optimized. It won't go beyond the expected range. Always that higher base width should keep in conductor spanning direction. Suppose the conductor is spanning this way, then your tower base should have maximum width in the conductor span. So if my conductor is spanning in this way, then my tower maximum higher width should be in the spanning direction. So this is a optimization in dimensioning. Then next one is profile selection. So suppose you are going to select an angle member or hollow section or any C profile or Z profile or any T profile to for a main leg or bracing, we need to first check the slenderness, because slenderness is a major property of compression strength. So that will define you whether the member is suitable for compression, because in a reversal force calculation, by considering the tension or compression, because the tower member are subject to reversal force, it means it will carry both the tension and compression loads. So compression is the major failure of any angular member. So we need to check slenderness first. Based upon the slenderness capability only, we can able to find out the exact the profile or angle size. Then we need to check the supplier catalog, whether the profile is available with the supplier for the certain span of a member. So if it is not available, we have to revise it from the design stage itself, or else once after going for fabrication, it is difficult for us to revise the changes. Next one is standards. Code exclusiveness is very important for gantry structure. We should not follow the general code for each nations or standards to be followed. Suppose ASC 0710 in American standard is for general code for loads calculations, like dead load, live load. It never have load calculation for substation projects. Also the load combinations, which is as per ASC 07 or IS 875 or European code EN 1990. So this ASC 07, IS 875, EN 1990 are load combination for general structures. But for substation structures, the load combinations, we need to refer only the specific code for substation structures. There are many specific code for substation structures in American standards, Indian standards, or Russian standards, or European standards. So these are the sample specific code for gantry structures, for substation structures, because ASC 113 will give you optimal load combination solutions. That is, a factor is less when compared to general code. That is ASC 07 2010. Similar, like in Indian standard 802 to be followed for substation gantry structure design instead of 875 loads and load combinations. Also for European standard EN 50341 part 1 to be followed for gantry structure loads for substation projects instead of general code like EN 1991 for load calculations and EN 90 for load combinations. So likewise, we have to consider the exclusiveness of codes, which is only suitable for substation gantries to be considered, or else what will happen, no? For other general code, the load combinations for live load used to have 1.5, but in this exclusiveness codes, that is specific codes, it used to have 1.2 of conductor tension. So optimization we used to miss if you are using the general code instead of this specified code. So these are the major points we need to consider for design optimization of any gantry structures. And these are the softwares and tools to be used for substation gantry structures. For design and analysis, generally we used to do in ETAP, SAP 2000, STAAD.Pro, robot structural analysis, Excel calculations. Excel calculation generally we need to do for two-way design, like base plate, anchor bolt design, stub design, and connection design if required. Even the connection design also we can do it in 3D softwares. Some of the software is having the stuff to handle the connection design. Detailing and modeling of gantry structures, we can use AutoCAD for 2D, advanced steel for 3D, Navy's work also for 3D, but we cannot able to do a detailed view in a Navy's work. It is for tentative view we can show it in 3D. Microstation 2D also possible and 3D also possible, but doing 3D in microstation is difficult for gantry structures, so it is better to go for 2D alone. And Tekla structures is a compatible tool to do these gantry structures. Then both 2D 3D, so advanced steel and Tekla structures can do having the possibility to do 3D drawings and detailed 2D drawing also. It is possible to do or generate GA drawings, shop drawings in advanced steel and Tekla structures, also the 3D drawings. Advanced steel and Tekla structures also provide the bill of quantity, automated bill of quantity. So that's all about this session. We will see in more videos. Thank you. Look description for more related videos. Subscribe to this channel to get a notification on more updates and videos. Thank you.